welcome all. I am Dr. Robin Abraham, belongs to Department of ECE, RKGAT. Today, I am going to present a topic, combinational circuit design with an examples of half adder and full adder. Because in digital electronics, there are two types of circuits. One is combinational circuits, second one is sequential circuits. So today I am going to explain one examples in which half adder and full adder will be explained. So first let me describe what is the difference between combinational and sequential circuit, because these two are very important in digital circuits. If you take a network which is having inputs and outputs, a combinational circuit whose output depends only on current input values. So the output only depends upon the current input. That type of circuits are called combinational circuits. So it uses only logic gates, means it will be implemented only with the helps of logic gates. When it comes to sequential circuit is different types of circuits in which the output depends on current and past input values. Okay, so you can see the difference between these two. Combinational circuit, the output depends upon present input, but in the case of sequential, the output depends upon present as well as the past. So it will be implemented not only logic gates but consist of storage elements, because a term which is called past input values. So if we need past input values, we need some storage elements. So that is the basic difference between combinational circuits and sequential circuits. So in which if you want to see the sequential circuit which is having a memory element as a feedback. Okay. Now I will tell you some examples of combinational circuits. So combinational circuits are having different types of combinational circuits are available. We can see according to the performance or operations. Okay, so one is arithmetic and logic functions, second one is data transmission, one is used for code conversions and all. So for example, in the case of arithmetic and logic functions, we can see different types of combinational circuits. For example, adders, subtractors, comparators, PLDs, programmable logic devices. So these will be used in arithmetic and logic operations in digital electronics. When it comes to data transmission, which is used in transmitting the data, digital data, in which we can see multiplexers, demultiplexers, encoders, decoders, all these things will comes under data transmission examples of combinational circuits. When it comes to code converters, means it will convert from one form of to another code. So in that, binary to gray code converters, some code conversion, BCD, binary coded decimal, then 7 segment, BCD to 7 segment, different types of code conversion. These three categories and these different examples are different types of combinational logic circuits. Okay, now we'll go to the important steps of designing a combinational circuit, because combinational circuit design we have a method, means we have to follow some steps. So how to design a combinational circuit? So first step is determine the inputs and outputs. So for every combinational circuit which is having a set of inputs and set of outputs. Okay, already we told that the output depends upon present inputs. Okay, that is combinational circuit. So first we have to, when we designing a combinational circuit, first we have to determine the inputs and outputs. For example, A, B. So these are the two inputs, X and Y is the outputs. Okay, so second one, assign symbol for each. So already I mentioned that input is A and B, output is X and Y. So we already determine the inputs and outputs. Then second, we assign the symbol for each, means inputs and outputs we already assigned. Then the third step, which comes the truth table. So truth table will define the input output relationship. Okay, so we have a set of inputs, we have a set of outputs, then we will derive the truth table. Okay, so the truth table will easily explain for the particular inputs what will be the outputs. Okay, then next step, we have to simplify, we have to get the simplified Boolean expression for each output. Okay, so already we have the truth table and we have the input and output relationship. Now depending upon, suppose there are one input, suppose there are two inputs, there are multiple number of outputs will be there. Okay, and we already know the relationship. So now using the k map, because the easiest, one of the easiest method to get the boolean expression is k map, Karnaugh map. So using the k map and using the min term, so depending upon, suppose the input is 3, we have to go for 3 variable k map. Suppose the input is 2, we have to go for a 2 variable k map. Suppose the input is 4 inputs are there, we have to go for 4 variable k map. So accordingly we can form the k map. Then we just input the min terms into the k map, then formation of groups, then from the groups we can form the equations. So that will give the simplified expression for the each output. Then from this equation, means we will get equations for each outputs. So the simplified equation, that is boolean equation. So from that we can easily implement the circuits logic diagram, that is network logic diagram, using gates, and we can finalize the design. So this is the method of combination circuit. So this method is similar to mostly all the combination circuit design. So these 5 steps are very important. Now I am coming to an examples, because in combination circuit adder is a important circuit. So adder is used in many circuits, it is very common, especially adders. The basic adders are half adder and full adder. So it is mentioned essential part of every CPU, central processing unit, because we have to do all arithmetic operations, we have to go for adders. So we have 2 types of adders, one is half adder and one is full adder. So half adder is here it is mentioned ignore the carry bit, because half adder consists of only 2 inputs. Okay, so it perform addition of 2 bits. So adder will perform, this half adder will perform addition of 2 bits, 2 inputs. And full adder, next type is full adder, it perform addition of 3 bits. So the difference between half adder and full adder is half adder consists of only 2 inputs, but full adder consists of 3 inputs. Okay, so we are going to implement these 2 half adder as well as full adder in this presentation and the design of both. So first let me go to the first adder, which is called half adder. Okay, so half adder is a combination logic circuit. Already I mentioned half adder is a logic circuit. It used for purpose of adding 2 single bit numbers. So we have only 2 inputs for half adders and we have 2 outputs. So it is already mentioned, it consists of 2 inputs and 2 outputs. The outputs we named as sum and carry. Okay, so sum is the addition sum and carry is the carry of the inputs. Okay. So if you can see the block diagram of half adder, you can see we have 2 inputs A and B and we have 2 outputs sum and carry. So this is the generalized block diagram of half adder. Okay, let me come to the design part of half adder, the designing half adder design. So first, already I mentioned earlier, we are going for the first step, that is identify the input and outputs. Okay, so first we identify the inputs. What is the 2 inputs variables, that is A and B. So here the inputs we are giving in the form of binary, okay, either 0 or 1. So one input is A, another input is B, and the output is S and C. So where S mentions, S is called sum and C is called carry. So we have 2 inputs, the A and B, and 2 outputs, that is sum and carry. So second step, draw the truth table. So already mentioned, first before going for designing any combinational circuit, we have to first form the truth table that will represent the input output relationship. So first A and B are the inputs and sum and carry is the outputs. So I will explain one by one the inputs. So if A and B, so here sum will, we already know the basic arithmetic operation, means binary addition, the same thing happening here. Okay, and we will have the sum and carry result. Okay, so 0 plus 0, so sum already we know that output is sum is 0, carry is also 0. When it comes 0 and 1, when it comes 0 and 1, the sum is 1 and carry is 0. And when it is comes A1, A is 1, B is 0, the sum is 0, sum is 1, carry is 0. And when it comes 1 and 1, because both inputs are high, means both inputs are 1 and 1, the sum is 0 and carry will be 1. So this is the truth table of half adder. Now we already know what is the next step. We have to form the expression, means to implement the circuit we need the expression. So the next step is K-map. So we already have the truth table for input output. So A and B are the inputs, sum and carry as the outputs. So now we have to form K-map for every outputs. So we have two outputs, sum and carry. So first we will form the K-map for sum. You can see this is the input, we have only two inputs. So it is a two variable K-map which consists of 4 cell, means 2 power 2, that is 4 cells, and this is the entry of result sum. You can see in this, you can see the min term. Here it comes M0, here M1, M2 and M3. So here you can see M0 we have logic 1 and M2 we have logic 1. Okay. Similarly in the case of carry also, this is the K-map for carry. We can see in M3 only we have the entry, that is 1. Now we already familiar with the grouping of K-map. Okay, so in this there is no provision of grouping, pair is not possible. So that's why these two min terms are individually grouped, and you can see the first group, that is an individual group, and you can see what is the relationship. So this is, I can say this is group 1, this is group 2. Okay, so the first group it gives A bar B, okay, and second one is A B bar. So if you go to the relationship, so group 1 and group 2, so sum is equal to A bar B plus A B bar. Okay, so we got the output relationship, sum is equal to A bar B plus A B bar. So if you look into this equation, that is similar to the equation of XOR gate. So A bar B plus A B bar, that is nothing but A XOR B. So that is given here, sum is equal to A XOR B. So we got the Boolean expression for sum. Second, we will go for the carry. If we go see the K-map, we can see an individual group and which is equivalent to AB. Okay, so carry is equal to AB. So we got two expression, one is for sum, that is A XOR B, and another expression that is for carry, that is AB, that is A and B. Now what is the last step is the implementation of circuit, logic circuit. So what to do is we have to implement this expression to using gates. Okay, so next this is the implementation, that is step 4, draw the logic diagram. So here you can see the implementation of half adder using one XOR gate and the carry using one AND gate as shown below. So now you can see these are the two inputs, and if you see our expression for sum is S is equal to A XOR B. So this is our XOR gate and carry is equal to A and B. So this is the logic diagram of half adder. So this way we are going to implement full adder also. So now I am going to the next topic, that is before going to the full adder, just we will discuss the limitations, advantages and disadvantages of these half adders. Okay, so we have some limitations in half adder. Half adder have no scope of adding a carry bit. That is a major disadvantage of half adder, because we have only two inputs A and B, and we have two outputs sum and carry. But when it comes for multiple bit addition, okay, this will not we cannot use this, because there is no provision of addition of carry in this. Okay, so that is mentioned here. Half adder have no scope of adding the carry bit resulting from the addition of previous bits. Okay, so when it comes for multiple bits, there will be carry generating, and that has to be carried to the next bit. So that provision in that cases we cannot use this half adder. This is a major drawback of half adder. This is because real time scenarios involving adding the multiple number of bits which cannot be accomplished using half adders. Okay, I already explained. So to overcome this drawback, we will be going for full adders, and that will be explained in the next slides. Okay. So now comes to some advantages of half adders. It is flexible and easy when it comes to design. Yes, we already design. It is very flexible, and is very less number of only one gate for sum and only one gate for carry. So very easy to implement, and it involves fewer logic gates. That is advantages. When it comes to applications, it can be used for addition, multiplication, means in microprocessor controllers and all, repeated addition will be used for multiplication purpose. So in low level addition multiplication, we can use this half adder, and it can be used in small integration circuits. So these are the typical applications of half adder. Now comes to full adder. So this is the next version of basic adders. Okay, that is full adder. So it is already mentioned, full adder is also a combinational circuit. Yes, and it uses for the purpose of adding two single bit numbers with a carry. So here one of the advantage, we have three inputs. Already in half adder we mentioned two inputs A and B, but in the case of full adder we have two inputs plus carry. Thus full adder the ability to perform addition of 3 bits. So full adder contains 3 inputs, 2 and 2 outputs. So we have 3 inputs and we have 2 outputs. The outputs are sum and carry. So come to the block diagram, you can see the inputs A, B and carry in. C in represent carry input, and the output S and C out. So S means sum, C out is carry. So this is a generalized block diagram of full adder. So come to the designing part of full adders. Okay, so same thing we already mentioned in the half adder. Same procedure will be following. In the case of full adders, we have input variables A, B, C in. So the inputs also in the binary form, that is either 0 or 1, and output variable sum and C out. So S means sum and C out means carry out. Okay. So now second step is the implementation of truth table. So here we have three inputs already, A, B, C in, and the outputs are sum and C out. So now just I will explain the truth table. You can see 0 0 0, the sum will be 0, carry out will be 0, and 0 0 1, sum will be 1, carry out will be 0. 0 1 0, the sum is 1, carry 0. 0 1 1 means sum will be 0, carry will be 1. 1 0 0, sum is 1, carry 0. 1 0 1, sum will be 0, carry will be 1. 1 1 0, again sum is 0, carry 1. And 1 1 1, 1 1 means 1 plus 1, that is 1 0, plus 1, sum is 1, carry is 1. Okay, so already we got the relationship, that is the truth table, means input output relationship is already shown in the truth table. Okay, so this is the truth table of full adder. So now comes to the next step, that is designing, means to obtain the boolean, means the output equations for sum and carry out, means the outputs. So now I will show. This is the step 3, that is draw K map using above truth table and determine the simplified boolean expressions. So this is the K map for sum. So this is you already it is already mentioned, it is a 3 variable because we have 3 inputs. So we have using K map 3 variable K map. Okay, so 2 power 3, 8 cells will be there. So the min term entries, it is already familiar here, 0 M0 M1 M2, sorry, M0 M1 M2 M3 M4 M5 M6 and M7. Okay, so this is the entries, means min term entries for sum. So it is mentioned, there is here also there is no scope of grouping the min terms. Okay, so all min terms are individual. Okay, so from this individual min terms you can just decode this. So we will get the sum equation is equal to, this is A bar B bar C in, that is the first one, then A bar B C in bar, second one, third one is A B bar C bar, A B bar C bar, okay, C in bar, so okay, then A B C in, A B C in. Okay, so 4 terms we got from the K map. Okay, so now this is a lengthier term, it is not optimized, so we need the minimum, means optimized Boolean expression. So in this equation you can see, if we take a bar common, it will be b bar c in plus b c bar, we can make it common. Then in this two term, if we make a common, it will become b bar c in plus b c in. Okay, so after looking this equation, means the reduced equation, again you can see here a bar, then b bar c in plus b c in bar. Okay, so this term, it is equivalent to XOR gate, because this is the formation of a bar b plus a b bar, that is the expression for XOR gate. So here instead of a b, here it is b and c in. You can see carefully, this is b bar c in plus b c in bar. So this become a bar as such, then this term become b XOR c in. Now comes to this one, here a is common and the common expression is b bar c bar plus b c in. So this is the expression for X NOR gate. Okay, so X NOR gate, the equation is a bar b bar plus ab. So instead of ab, here it is b c in. So here you can see b bar c in bar plus b c in. So this term will comes to b X NOR. This is X NOR gate, b X NOR c in. Okay, so we already know that XNOR, we see XNOR gate, if we inverted, it become XOR gate. Okay, so I can say A XOR B, A XOR B is equal to A XOR B bar. Okay, so here you can see the first term a bar common, then b XOR c in, then plus a, and this is XNOR. So the how can I convert this? I converted to XOR and I put a bar. Okay, so b XOR c in, that is XOR gate. If I put a bar over that, it become XNOR. Okay, now if you look carefully this equation, you can see this term, entire term is equivalent to XOR gate equation. Okay, you can see a bar and the second term is b XOR c in plus a, and second term is b XOR c in bar. So this is equivalent to our XOR gate same equation. You can see a bar, this b XOR c in is our term b, and you can see this is a bar b plus a, this is b bar. Okay, so if we both add together, what it become? It become the equations of XOR gate. So it become a XOR b XOR c in. So we form the equation for sum, that is sum is equal to a XOR b XOR c in. So this is the optimized result of sum. Okay, a XOR b XOR carry in. Now comes to the next K map, that is for the carry out. Okay, so this is the entry for carry out. So K map, we have 3 variable K map. Okay, and we have 8 cells and the entries in 3, 5, 7 and 6. Okay, so we can see we have 3 groups. Okay, here there is a provision of grouping all the min terms in 3 in the form of pairs, means pair means 2. Okay, so you have the first group, this one. Okay, so the output is a c in, because we can see this is yes. So this is a bar, this is a. So similarly this is b bar c in bar, this is b bar c in, b c in, b c in bar. Okay, so So if you see this, these two groups means 5 min term 5 and 7, that groups that is belong to A and C in. Then min term 3 and 7 that belongs to B, C in, and min term 7 and 6 and 7 that goes to A, B. So if you got the addition of all these three groups, we can finally obtain the C out, that is C out is equal to AB plus BC in plus AC in. So this is actually one of the output, simplified output equations of carry in terms of full adder. Okay. So if we can further reduce this one, we can again we can reduce it. So what to do is, first we have to convert this C out into a standardized SOP. Okay. So if you look into this equation, so C out equal to AB into C in plus C in bar plus BC in into A plus A bar, then plus A C in into B plus B bar. So what to do is, we have to multiply the each term with the missing term. So here the missing term is here, first term C in is missing, so I put C in plus C in bar. So this is actually nothing but 1. So second term B C in is missing term is A plus A bar, so this is also 1. A C in and missing term is B plus B bar, that is also 1. Then we will expand this. Okay. If we will expand this and make this common, if I expand, this become ABC in plus ABC in bar plus ABC in plus A bar B C in plus A B C in plus A B bar C in. So if we expand this one, this will be the equation. So in this we have some common terms. Okay. So if we take, there is A B C in is common, so we will take once, so that is this one. Okay. Then remaining terms will be there. So our final equation will be A bar B C in plus A B bar C in plus A B C in bar plus A B C in. Okay. So finally the equation will consist of 4 terms. Okay. Now if we make common this A B terms will be common. So here we can see A B. So we C in will be common, C in plus C in bar will be common. So A B into C in plus C in bar plus here C in is common, and remaining terms are A bar B plus A B bar. Okay. So after taking these common terms, finally we obtain A B into C in plus C in bar is nothing but 1. So A B into 1 is A B. Then C in into, here you can see A bar B plus A B bar. A bar B plus A B bar is nothing but A XOR B. So you can see first term is A B plus C in into A XOR B. So our final equation for C out is become A B plus C in into A XOR B. So these two equations we can use it for C out, either this first equation, that is C out for is equal to A B plus B C in plus A C in, and also we can use this one. This is the optimized one, because after I'll show in the next slide. Okay. So C out is equal to A B plus C in into A XOR B. Okay. So we got 2 equations for the carry out of full adder. Okay. Now going to the implementation of the circuit. Already we got the equations for sum as well as carry. So we are going to implement. So the sum, the equations is A XOR B XOR C in. So that is implemented using two XOR gate, because we have only two input XOR gate. Okay, so first two inputs A, B is here, so we will get A XOR B, and that output is connected to another XOR gate where we are giving another input is C in. So the final output is sum is equal to A XOR B XOR C in. Okay, so that is the sum output. So it is mentioned S is equal to A XOR B XOR C in. Now the logic circuit for carry out. So AB plus BC in plus AC in. So here we have three AND gates. The first AND gate for AB, second for BC in, and third for AC in, and these three will be added using an OR gate. Okay, so finally we will obtain AB plus BC in plus AC in. So this is the first method of implementation of carry out, and sum is there is no other circuit because output is A XOR B XOR C in. Now why we derived the second form of carry out, that is explained by this diagram, because the second carry out is A XOR B into C in plus AB. Okay, so now you can see this is the implementation of full adder using two half adder. Okay, so here you can see this is the diagram of a half adder 1, this is the diagram of half adder 2. Okay, so half adder 1, you can see we have two inputs, it will produce okay, so this will produce A XOR B. Okay, and here you can see this first half adder will produce carry AB. Okay, so here you can see the output of first half adder is connected to second half adder. So this is A XOR B, and here we are having C in is there. So the output, final output is A XOR B XOR C in. And now it comes, there is another AND gate. So one of the input is A XOR B, another input is C in. So this output is A XOR B into C in. Okay, and another input is AB. So we have another OR gate. So finally we will get C out is equal to A XOR B into C in plus AB. So this is the another optimized output of full adder. Actually we have implement, we can say we can implement a full adder, one full adder using two half adder. Okay, so that's why we derived the second equation in the previous slide. Okay, so you can see the output is A XOR B into C in, that is a carry output A XOR B into C in plus AB, and sum is A XOR B XOR C in. So and this is the representation in the form of block diagram. You can see first half adder, it will produce carry out AB and produce sum A XOR B, and that sum is given to our second half adder, it will produce sum is equal to A XOR B XOR C in and C in is given to second half adder, so it will produce this same output. So this way we can design the full adder. Okay, so I think now it is clear for you the design of half adder and full adder. Now before concluding the session, I am going to explain the discuss the advantages, disadvantages and applications of this full adder. So what are the advantages of full adder? So one of the advantages, it can add 3 bits, include one carry input and carry output, which can perform more elaborate calculations, computations. So that was one of the in the case of half adder we don't have the carry input calculation. So here we have the carry input also. So in multiple, means when we are going for multi-bit addition, this will be half adder, full adder will be useful. Okay, it can be cascaded to produce adders for a number of bit addition, which makes suitable for multi-bit, means parallel adders, different types of adders which are using full adders because the provision of carry input. Okay, and drawbacks, it is little bit complex because we have more number of gates, making design more complicated and expensive. And it is also slow because we have two gates, because the some output which is having two gates, XOR gates, okay, and instead of one, so it will be likely delay will be there. And come to the applications, it will be used in carry look ahead adders in digital processors that utilize multi-bit binary addition, present in arithmetic logic units, ALU, and other complicated digital system. So that's all about half adders and full adders. I think it is clear for you the half adder and full adder design. And when it comes to combination circuits, the other circuits also, we have a lot of combination circuits in digital electronics. All these digital circuits, the design concept is same, because the same thing will go, first we'll go for the truth table input output relationship, then we'll go for the K map, then realize the logic circuits. So thank you very much for listening my session. Thank you all.